to all of you for coming. Thanks to Rahul and Christina for inviting me here, giving their presentation. It's about Turing mixtures and Turing foams. Basically, that's about how you can frame protein pattern formation that you find in cells in terms of those two concepts. So let me show you some interesting patterns that you observe in cells. So here that's a yeast cell, and what you should observe is this polar cap here. That's a protein pattern, and this protein pattern is a template for actin cables, and those actin cables here then produce the bud site. So this pattern that you see is responsible for budding cell proliferation in yeast. That's another famous example of protein patterns, is the oscillations of min proteins in E. coli cells. As you can see, they go back and forth between the two cell poles, size about 2 microns here, and that's responsible for defining midplane in E. coli cells such that the FTS ring can form, creating cell division. The third example is more intricate. It's a coupling between protein patterns and the deformation of the actin cortex of the starfish oocyte. So here you see on the left, as the movie loops, the pattern of the row waves in green, and that's then connected to a deformation mode of the actin cortex. And finally, this is recent work with Petra Schwille's group. That's a pattern on a surface, which is again the min pattern that you see here on the left, just in a in vitro situation, and that foamy-like pattern of the min system is able to actually create forces such that you make whole vesicles move by a pattern. All right, so that's the motivation for doing all that, because there's such interesting range of patterns that you see. Let me focus down on the min proteins. Here it's basically, and that's the beauty of the system, just 2 proteins driving the patterns that you see here, and the reaction network is like so. It has a few key principles which are the same, not just here, but also for other pattern forming systems, like the example you saw for yeast. So the story goes like so. You have, sorry, let me go back. Sorry, pushed the wrong button. So the story is as follows. You do have 2 proteins called min-D and min-E. This min-D is an ATPase, so it has to transform from the inactive to the active state before it can bind from the bulk, the cytosol, to the membrane. Once bound to the membrane, there's a positive feedback loop that recruits more of the min proteins to the membrane. And that would just lead to accumulation of min-D proteins on the membrane. So there's a second protein, min-E, which is also recruited to the membrane by the min-D proteins, forming a dimer. And in this dimeric form, the min-E hydrolyzes the min-D, making it inactive again. So both of them, as you see, fall off from the membrane, go back to the cytosol. So what you have here is the cyclic flux of proteins between the membrane and the cytosol and back. And that will be the key theme of what I'm going to talk about in this talk. The math of it is interesting, but not so easy. So what you have to solve is diffusion reaction equations defined on the membrane, so a 2-dimensional surface, and defined in the bulk, so a 3-dimensional volume. And you have to couple the 2 diffusion reaction equations by a so-called reactive boundary condition, which says that any kind of diffusive flux that you might have is balanced by the reactions between the bulk and the surface. And you have a geometry where you have this typical shape here for the E. coli cell. Now, if you take this innocent looking protein pattern that you see here, which just does this nice oscillation to define midplane, you take it out into a artificial reconstituted system. So for example, in a wedge-like system like so, then you see on the computer, if you simulate the system, all kinds of patterns. If you look at it, you see spiral waves, you see standing waves, you see traveling waves, you see some kind of turbulence here, if you want to call it turbulence. Then this turbulence sneaks in and tries to take over. So in a second, I guess you see some kind of a flame front-like behavior taking over the whole sample. And then it looks as if this would be the stationary state, so you would have some turbulence, but no, after a while, there's still some dynamics going on, and in the end, as you look at it, you will see some pattern which is similar to a smectic with all kinds of defects in it, like dislocations. That's not just the nightmare of a theoretician, it's also realized in experiments. This is the group of Kees Dekker at TU Delft, and they just did the very same experiment, putting the mean pattern in such a wedge-like shape, and they see the same kind of phenomena as you see in the simulation. All right, so that's to motivate you to see that this is a beautiful range of phenomena that you can study theoretically. And now let me focus down on one particular, very simple, but also very important issue. And that's mass redistribution in the system. So if you boil it down to the essence, you can say, I just look at one protein, and this one protein has two states, one on the membrane and one on the cytosol. And if you do so, then the total density is just the sum of the protein density on the membrane and the cytosol, and the reactions that you can write down in its simplified form, let's say in one dimension. It's just the diffusion reaction equation of that type. It's basically Turing's model with a catch, and the catch is that these are not two different functions, f and g, but the function g that Turing had must be minus f, since the system is mass conserving. Okay? And because it's mass conserving, if you add the equations up, you do get an equation for the total density that just contains gradients in the cytosolic and the membrane concentration, and the reaction terms obviously cancel out. So you can write it, if you like, in this form, where you find this eta here to be a potential that we call a mass redistribution potential, and that drives the dynamics. Now it looks as if this would be very similar to model AB and whatnot, but there's a difference. The potential that you see here is not one that's derived from a free energy. It's also not one given as a functional. It's actually given something by an equation of motion on its own that's coupling back to the dynamics of the membrane concentration and the cytosolic concentration. Okay. Now to illustrate of what could happen here, let's look in phase space. And here you have the concentration in the cytosol on the membrane. Here's some N-shaped nucline like we had it yesterday. And then there's two planes that are important to surfaces. One is the surface of the equilibria, the nucline, and the other one is the surface of mass conservation, which is a simplex here. Now, as you look at that, there is a fixed point. Let's say it's stable. This fixed point depends on the nucline shape, but it also depends on the total number of proteins that you have. Right? So it means you have now the total protein concentration as a control parameter in your system, and as you change it, you change the equilibrium. The point, as you saw in the previous slide, n is not a static variable, it's a dynamic variable, so you redistribute it, and that then affects the equilibrium as you see here from this graph. So let's make a brutal assumption and say this nucline is a kind of a scaffold, and that scaffold attracts all the flow, such that we can replace the concentrations, which are dynamic, by the fixed point concentration, so the values along that nucline. It's a kind of adiabatic approximation. It's more than that. It's a scaffold, because here the shape of the flow is not changing much if you wouldn't do this. It would change a lot if you were to have something that has multiple minima here. So if you do that, you can just insert that into the equation of motion for the total density, and then you do have a closed form expression. That's the nice thing. Now you have an equation for the density that's given by a functional of the density and corresponding differential operators. So let's apply the chain rule, and then you see that you can write this in this form, which has two important parts. One is a nonlinearity. That's not so important. The linear term is quite important here, because it tells you this looks like a diffusion equation with an effective diffusion coefficient. And now you can understand the pattern-forming mechanism simply as, well, negative diffusion. So once this gets negative, you get the homogeneous state being unstable. And that condition, if you rewrite it mathematically, is just turning into this criterion here that this ratio of the derivatives of the reaction rates has to be smaller than the ratio of diffusion coefficients. And you can turn that into a slope criterion in phase space. So this says you will have a Turing instability in the system if the slope of that null line is actually cutting this here in an abstruse way. Okay, so that's the criterion, and it's a very straightforward way of characterizing the pattern formation process here. You can look at this now in phase space when you study the system in time. So let's look at that. This is phase space. This is the null line. That's the simplex. Here, this is the same on the membrane density, so in physical space, and here on the cytosol also in physical space. And as I let the simulation run, you'll see that you have redistribution instabilities that form a pattern, which is very reminiscent of a Turing pattern, with the fastest growing mode being the wavelength. But over time, system is not stable, there is coarsening, and after a while, you just get a system that has a low density phase and a high density phase, and no longer any kind of periodic type of pattern. There's more. If you look at that, you can map out the space on which this pattern lies. It lies on this flux balance subspace where the fluxes in the reactions balance. And there are certain points that you have in this flux balance subspace. I number 1, 2, 3, and they correspond to the plateaus of this step-like pattern and its turning point. And you can translate that into a phase diagram by looking at the construction here, and then gives you then a bifurcation diagram, which is quite reminiscent to what one finds also in phase separation with a quote-quote binodal and a binodal regime in phase space. All right, so that's a short story about the most simplest system you can think of. And now let's go further, but before I make some general observations. So one observation is that you do have this negative diffusion, so anti-diffusion, which drives pattern formation. That's a key point. The patterns are characterized by interfaces. So it might be worthwhile, and that's what I'm going to do next, to study what these interfaces do and what their properties actually are. Depending on the model, you can get all kinds of things. So you can get phase separation and coarsening, traveling and standing waves, as you saw, spiral waves and turbulence. So it's a very broad range of behavior. And last, and that's also quite important, these models are not just cooked up, they actually compare well with experimental data, and you can compare this with in vivo and in vitro data. I will not talk about this because I just don't have the time. So let's now look at that. Interfaces is something you know interfaces from bilayers. There's this beautiful paper by André Koschmill's group that shows multi-component mixtures with a corresponding demixing behavior. There are interfaces organizing it, and there are interfaces in foams, in liquid foams, as in this example from Cessna's and Durian's group, as you see. Well, do you have those kind of phenomena also in non-equilibrium systems, despite the fact that here you have surface tension, of course, and in the other system, there's no obvious surface tension because there is no basic mechanical interaction between the particles when you do pattern formation. So let's look just into what we know about phase separation in these systems. It's driven by gradients in the chemical potential. There's this famous Gibbs-Thomson relation that just relates all the osmotic pressures that you have in the system to the Laplace pressure. So here you have the jump in all the densities of your different components. That leads to shifts in the chemical potentials because of the curvature. And this curvature kappa here is on the right-hand side for the Laplace pressure, and sigma is the surface tension. It's a very famous relation, also a very important relation, because based on that, you can construct the theory of Ostwald ripening and understand coarsening behavior in standard multi-component liquids. If you look at pattern formation, there's also interfaces as I showed you. Here I show you another example for the PAR system in C. elegans. It's simpler than the system, the MIN system that we looked at, because here you have two proteins that also attach from the cytosol to the membrane, but once they're attached, they kind of fight each other, kicking each other off. So there's an antagonism between the two proteins, and that gives rise, as you see in this nice experiment by Stefan Grill's lab, to this bipolarity in the C. elegans zygote. The point now I want to make is if you simulate that, then you have an interface, and this interface shows dynamics, and as you see, it minimizes length. It always finds that part of the ellipsoid that you see here with the shortest path for the interface. So there seems to be the essential ingredient of surface tension, namely that it minimizes length of the interface. But what's the origin of a surface tension in such a diffusion reaction system? And that brings me to the most important slide of this talk, and I'll guide you through because it's really important that you understand this here. This is the basic idea of all I'm going to talk about in the following. Okay, so here you have an ellipsoid. There is a pattern on the membrane in dark blue, going from dark blue to a light blue, and that's shown here in this sketch as the membrane density going from a high value to a low value. There will be a corresponding pattern of the cytosolic protein just in the bulk, you don't see that here, that goes from a low value to a high value. The reason you have this interface is anti-diffusion. That kicks off the homogeneous steady state into an inhomogeneous behavior, but once you have it, the interface is maintained by the following. You have reactions that, as I told you, cycle the proteins between the membrane, the cytosol, and back. So that's continuous cyclic flow or current driven by the ATPase cycle of the proteins. So what you have is, if you're here at the foot of the membrane density, you have a low density, so you have a flux of proteins on the membrane back to the cytosol by reactions. Once they are in the cytosol, they diffuse, because there's a gradient here in the cytosolic concentration. And then on the other side, on the foot of the cytosolic concentration, there is an attachment zone where you have proteins from the cytosol coming to the membrane. And again, here on this side, you have diffusive fluxes on the membrane, and that means you have two counteracting diffusive fluxes on the membrane in the cytosol, and they are maintained by these reactive fluxes on the two sides of the interface. Okay, so that's what you have, and the origin of that cyclic flux, as I told you, is the non-equilibrium nature of the chemical reaction driven by the ATPase cycle. If you switch off the ATPase cycle, you lose this beautiful interface here. All right, now what does that mean in terms of a curved surface? So let's look at that. Now I'm on the membrane, and I'm looking at a curved interface on the membrane. So again here, this is high concentration of membrane proteins, and that's low concentration, and the bulk is underneath. So it's looking onto the surface of this membrane. So here on the boundary of that interface, there's this layer where you go from high concentration to low concentration, and this interface layer has some width that I call L-int. Well now, as you imagine going from a straight configuration to a bent configuration, you're changing the geometry in a very simple way. Just look at the figure here. If you take a positive curvature, then the outer part of this interface, the detachment zone, gets larger. And the attachment zone here in the back gets smaller. And vice versa, you have it here in a region where you have a negative curvature. Okay. as you have a higher zone here of detachment and a smaller one of attachment, you will have a flux, a surplus of proteins going from the membrane to the cytosol. Okay? And the opposite here. So that means in total, if you take it together, there's going to be a higher concentration of proteins on that side where you have positive curvature in the cytosol, as opposed to that side with negative curvature where you have a lower concentration. And that means, by Fick's law, you have diffusive fluxes from that zone to that zone, filling up the void that you have here in the interface, and that makes the interface flat again. Okay? Right? So the surface tension comes through cytosolic fluxes and this maintained cycling of proteins between the membrane and the cytosol. There's no interaction here. It's just non-equilibrium fluxes that move this interface. After all, the interface comes about not by interactions, it comes about by the presence of these non-equilibrium fluxes.
Excuse me.
Yeah.
Can one measure the fluctuations of the height of the surface while this is going on? And
you mean the membrane or you mean the interface?
membrane.
So for typical systems like the vesicles Petrashvili is looking at, they are GUVs, and they do have some fluctuations. You can measure it by different methods. It's not something which plays in here, I would say. So I assume the membrane surface to have a fixed geometry, and there's no fluctuations in the membrane. If you would have fluctuations in the membrane, you would have feedback on what's going on for the diffusion reaction system, because as you fluctuate the membrane, you change the metric tensor. By changing the metric tensor, you change distances, and that changes the diffusion operator. That's not what I do here. All right, so I hope you got the point of this, and that means you have a Gibbs-Thompson relation that comes from reactions, which says that these kind of gradients, the shifts in the concentration of the proteins in the cytosol is proportional to this area change, and that's proportional to the width of the interface times the curvature. So I'm saying the interface tension here is simply proportional to the interface width, or in other words, it's proportional to the diffusion constant of the proteins on the membrane, since that defines the interface width. All right, so let me go and study the implications of that interface tension, this reactive interface tension. And let's first look at a generalization of this PAR system. It's basically a generalization from a binary system to a multi-component system in the same way as you would generalize a binary mixture to a multi-component mixture. So instead of just mutual detachment of two pairs of particles A and B, you consider a set of particle types, A, B, C, or even more, and you make them interact such that there is some self-reactions, meaning attachment, detachment, and there's mutual antagonism between the two proteins, here encoded by this arbitrary choice of reaction terms between the components A, B, and C. Then you do write down the equations for the two components in terms of this here. And as you look at that on a computer, then you'll see over time, it shows the mixing type of behavior in very much the same way as you would have it for multi-component mixtures. And in particular, in the end, you end up with these vertices that are a meeting point of three different phases in the system. So question is, are there interface laws? Can you design these kind of patterns? And what kind of coarsening dynamics do you have? Is this all similar to phase separation in thermodynamics, or is there some interesting difference? I wouldn't be here if I wouldn't tell you there's a difference, so let me explain to you the difference. Here's again our toy system. so a multi-component reaction system with mutual antagonism. And for that system, you can actually go through the math, meaning you can analyze everything in terms of these concepts of a mass redistribution instability. You can create an interface theory, and you can go through all of that basically analytically and fairly rigorously. That's something you find soon in this paper by Henrik and Tobias, who are the students that did that work. So the outcome of that analysis is, so remember I introduced eta as the analog of the chemical potential. It's this non-equilibrium mass redistribution potential. And what the relation that you get is, it's stating that the difference, the shift in the mass redistribution potential for particle type A and particle type B is a relative sum. The minus here comes because they are antagonistic. That's why you have a minus. And then on the right-hand side, you do get what's typical for a Gibbs-Thompson relation. You get a surface tension, you get the curvature, and you get the gap here, the jump in the density of the particles, here the A particles. The surface tension, as I say, is related to the interface width, which is given by the maximum of the diffusion coefficients of the A and the B species on the membrane. And here's a check. And that just shows you that the calculation that Henrik and Tobias did is right. If you compare that with simulations, it's this linear relation that you find of the shift in the mass redistribution potential with the curvature of a circular interface that we study here. Right, so there is this Gibbs-Thompson relation, and it looks very much the same. The origin, of course, as I said, is different. The sigma, again, is coming from reactions and not interactions. So now, there are other laws that you know that are true in foams or in mixtures. And one of these general laws is the Neumann law that applies to steady state. It's simply saying that if you look at a vertex here, then the surface tension that go out from that vertex, they need to balance. So the sum of these forces needs to be zero. And that's basically because in thermodynamics, the equivalence of surface tension and the equivalence of osmotic pressure at that point are the same thing. Right? This is no longer true in the system that we study, because there, the reason for the surface tension is not in thermodynamics, it's in fluxes. And these fluxes, they are different along the boundary between the two interfaces and in the core of this trefoil junction here. And because of that, you can show, again, I'm skipping the calculations, that the Neumann law has an additional term that I call F core. And I'm telling you, it's basically the curl of the reaction terms on the right-hand side that you saw in the previous slide. Okay? So it comes from things that you cannot write as gradients, but that are due to curls in the reaction terms. All right. If you use that, you can actually ask yourself, can you implement with all that non-equilibrium behavior also interesting phase behavior? And here's one intriguing example that I picked. So what Henrik and Tobias did here is they looked at a three-species system, and they changed the rate at which these species mutually repress each other on the membrane. So you can tune how much A, B, C like each other or dislike each other. And what they could do is they could tune the angle between the A phase and the C and the B phase such that you can go all the way to what's called complete wetting in the literature on multi-component mixtures. Okay? So that's one phenomenon that you can get. And here are a multitude of others where they can show that if you pick different kinds of interaction network between the different species A, B, C, and D, you can basically at will design different patterns with different types of interfaces between the different species in the system. What's the coarsening law? Well, it's the same actually as the coarsening law for a Ostwald ripening process. So here are the data. That's the typical size of these structures as a function of time. and you get this famous LSW law of t to the 1/3. What's a bit weird, and for that I don't have an explanation, so maybe Cesare you have, or anybody else. It's not clear in these systems, what the forces really are, because the phenomena come about by reactions and fluxes and not by mechanical forces. So what we asked ourselves is, if you look at the system here and look at all these threefold junctions, what's the force pushing these threefold junctions? You could say, well, you just showed me the generalized Neumann law, just take that and take the deviation from that and use it to calculate the direction in which the threefold junctions are pushed. That's not correct in the data. In the data, what we see is that the forces, quote, quote, forces that push the vortices here is actually the sum of the three terms that comprise the surface tension, the non-equilibrium surface tension. And the core term that defines the shape of the junctions is not relevant. So it seems to be that what determines the shape of the junction and what drives the junction's motion is given by different types of tensions and forces, effective forces in the system. Now last, we wanted to see how this toy model, yeah?
So you said in this situation you always have coarsening. So are there any conditions for the K coefficients that you have to not, let's say, get your coarsening arrested?
There are two ways of doing that. In these simple models, you basically have to break mass balance, the conservation law. That's an easy way of getting coarsening arrest. Another way of getting coarsening arrest is if you look at different kind of chemical networks, as the one I'll show you next, like the MIN system. It's complex enough that system no longer has coarsening.
You say for the pairwise, I mean, now you
Yeah,
have
for the simple, for the pairwise system, it's basically always coarsening. And there's a mathematical reason behind that. It's a lengthy calculation that Tobias and Hendrik did, is in that case, there's actually a generalized functional that you can define, and you get back to some effective gradient dynamics that helps you out. Yeah. Okay, now let me come to real systems, meaning MIN systems, those that we saw early on that gave rise to the MIN oscillations and also gave rise to this beautiful range of patterns in the in vitro situation. Here, that's another pattern those MIN proteins show, and they show many patterns just depending on, how much concentration of MIN-D and MIN-E you have, how you label the MIN proteins. That means how you actually determine, fix their rates of attachment, detachment, and mutual interaction. Here in that regime, they found these labyrinth-like patterns. Okay, you look at them, right? You see this looks very much like a phone. You have bubbles with 5, you have bubbles with 6 and 7 edges. There's something different from foams that you would never see in foams, which is this. Right? So this is something inside a bubble, not connected to the boundary. You couldn't have this in the liquid foam, and there are many of those. If you start seeing one of them, you start to see many of them. Okay?
What is the length scale on this picture?
That's actually, I don't know by heart. It should be something on the size of microns, roughly. Microns, tens of microns, yeah. Okay, now, are these foams? Well, you can study by looking at statistics of it. So you look at all the threefold junctions, and you just measure the angles. And what you see is here you have pretty much, with a very small standard deviation, 120-degree angle between the different boundaries. That's very much like a foam. That's a characteristic feature of a foam. You also see, if you look at movies of this system, that if you look at fourfold vertices that you have here, they're unstable, they move apart. and you get an additional boundary. That's also like in a foam. This here is again a feature which is reminiscent of foams, namely that's the number of corners or edges that you have, and it's centered around 6. So typically you have hexagons and pentagons, and heptagons are rare or less frequent than hexagons. What's different to foams is that you get an equilibrium distribution of bubble sizes. So the system shows coarsening arrest. It's not coarsening to the end, but you have a finite length scale and this distribution around that finite length. Well, now we wanted to test that using our model for the min proteins, and as I told you, this is a model that is quantitative and you can compare it well with data in vitro and in vivo, so it's kind of a good test system to also check whether our computational model shows pattern formation. Here there's a few additional interactions that are not so important for those that are experts, but in addition to the min proteins doing the cycling, there's 2 different states of min E in addition, and there's some reaction that makes one of the proteins reside longer on the membrane. So there's 2 additional features here that you need to be quantitative in order to compare with the data. Well, you find the same kind of patterns, you find the same kind of 120-degree angles, and you find the distribution of edges also centered around 6. So also on the computer, this is a nice form. Now you can use the computer and these numerical representations of the experimental system to study what is underneath the coarsening dynamics and how does coarsening arrest. The first experiment that Hendrik and Tobias did is they took a computer simulation and then they shrank it down by a factor of 2. And then they asked, okay, if you shrank it down, is it expanding back again? And how is it expanding? What's happening? Well, try to look carefully. So look, there's 5s, 6s, and 7s. And you will notice that 5s shrink and 7s grow. And that's not an accident, because behind that very fact is a geometric law that you cannot beat. I'll tell you which one. So we know from this very simple argument that I showed you that the currents are maintained by these fluxes, then there's flows, there's boundaries moving, and those boundaries moving will always have a velocity that's proportional to the curvature. Okay? That's all you need to know. If this velocity is proportional to curvature, you can use it to calculate the change of area of these bubbles with different numbers of edges, because that's just a boundary integral with the velocity, and that here you can write as a boundary integral with the curvature, but that's just the Gauss-Bonnet theorem that you have now. And once you apply the Gauss-Bonnet theorem, you'll find that the change in area needs to be n, the number of edges, minus 6, and some constant in front of it. So differential geometry is bounding what you have, and that's reflected in the data. The data show the very same behavior. The 6s stay constant, the 5s shrink, and the 7s grow. And that's very analogous to what's called the von Neumann law for coarsening dynamics in 2D deforms. It's the same law, it has the same origin, meaning this geometric effect, but the physics underneath is reactions and not interactions. So we have seen that. Coarsening is by von Neumann's law. What about the back reaction? Because you need it, right? If you just have coarsening, you would go back to a foam that coarsens to the end, and you would lose all the cells. So what's happening that counteracts the coarsening process? And now I come back to these little blips that you saw in the min patterns in between the bubbles. So look at it here. So there's 2 cases that I call I and double I. Let's look at that first here. You see, after a while, when this bubble here grows, over time, there is a nucleation happening in the middle. This nucleated min proteins, the E here in this case, they extend into an interface, and then you have a new boundary. So by creation of nuclei and their expanding, you create new interfaces. You can also have a second process where you start from such a bubble, you make it grow, and then there's some kind of surface instability.
With tunnels.
Yeah, and the surface instability is not clear yet to us what drives that. But if you look at our argument is based on the fact that there are diffusive fluxes, there's attachment and detachment, they all depend very much on the rates. And if you choose the corresponding reactions properly, you can create positive surface tension, as I explained it. But of course, you can also create negative surface tension. And then you're back to an instability of the interface, which could give rise to a phenomenon like so, where this interface here splits off and creates a new boundary. All right. Now, where do we go from here? I told you this at the very beginning. The pattern that you see here, this greenish pattern, is the very same min pattern that I showed you earlier, that I explained in terms of this theory of foams in reaction diffusion systems. Here's a cartoon. So that's the pattern of the min proteins. And on top of that pattern, you have a vesicle. And that vesicle is just a lipid bilayer. And of course, also on top of the vesicle, you do have the protein patterns that's covering it as well. So as you saw, this vesicle is moving. So you're able to transduce the energy that's in the chemical pattern into active motion of the vesicle. There's no motors, there's no actin cytoskeleton, there is no, how should I say, things that push here, like in the cytoskeletal system. The reason for that motion is different and not fully clear to us yet. So as you see from the motion, you also see that in the wake of this vesicle, you have the deformation of the patterns. They seem to accumulate here basically on the rim, and it looks like the min pattern is pushing it. At the moment, there are two ways of explaining that. One way of explaining that is that the min proteins, which are on the leaflets of the bilayer of the vesicle and the leaflet of the supported lipid bilayer, that they are interacting, and you have a kind of a zipper effect that pushes things forward. There's another quite intriguing explanation as well, and that's known also from data by Petra, which were interpreted by Reinhard Lipowski, namely that as those min proteins bind to the lipid bilayer, they actually create spontaneous curvature. Okay? So as you have a high density of these min proteins in the back, you change locally there the spontaneous curvature of your system, and that couples into quantum Helfrich theory as an additional term. And that could also give rise to such a force that drives the vesicle forward. Both work. You can test it in computer simulation, and here's one by Tom Burkhardt in the group, and you see it creates the same kind of motion. All right, so let me conclude. I hope I could show you that there are interface laws of Turing foams and mixtures. And these laws are based on a non-equilibrium surface tension that's created by cyclic fluxes of attachment and detachment along the interface of these patterns. They give rise to a set of laws. There is a reaction-driven Gibbs-Thompson relation, which is basically Neumann's law plus, namely plus curls of reactive flows, this core term here, coming from the non-gradient nature of the reaction terms. You can use that to design the morphology of these reaction diffusion systems in the same way as you can design the morphology of multi-component mixtures. There's another law, in addition to Gibbs-Thompson's law and Neumann's law, there's von Neumann's law, which is basically a geometric law following from Gauss-Bonnet theorem, and the fact that the surface tension that we have gives rise to something that depends on curvature. And the counteracting agent for Neumann's law is, as I told you last, the nucleation of small little patterns in between bubbles and interface kind of instabilities. Let me thank the people. I think I want to single out two guys here, namely Henrik and Tobias. It's really their work that I mostly talked about. And Tom's work I mentioned only at the end. He worked on the vesicle moving on the supported lipid bilayer. And of course, I want to mention Fridtjof Browns and Jakob Halatek, who developed the scheme of local equilibria theory with me already some time ago. And these are my colleagues whom I owe a lot of thanks because they keep us honest as scientists and make us compare our theory with data. So thanks for your attention.
Questions?
Can I ask what was in the simulation for the moving vesicle?
How was it done?
Yeah, I mean, in the sense that how was the vesicle talking to the...
Yeah, so it's a difficult problem because what we did not do is we did not simulate a moving boundary problem because that's too hard.
Yeah.
You need to solve the numerics for a change boundary all the time, keeping track of all the boundary conditions. So what instead Tom and also Jan Willeke in the group are developing is a phase field method where you say our membrane is not a boundary, but given in terms of an auxiliary field, a phase field similar to what people have done for cells or crystal growth. And then you can reduce the set of equations to a volume partial type differential equation, and that's solved by finite element methods.
And how was the mean talking to, I mean, did you put a coupling between the...
An ad hoc coupling.
Ad hoc coupling.
Yeah. So the ad hoc coupling was just saying if there is more of mean E, then do this. We don't have a full theory of the interaction yet. That's the missing link. Yeah.
You possibly say this, but I maybe missed it. When there are proteins attached to the surface, they can also do a random walk on the surface. And is that one of the diffusions you already have in the problem?
Yeah. So the proteins in the cytosol diffuse by 10 micrometers square per second. On the membrane, they diffuse as well, much slower, 0.01 or 0.001 micrometers square per second. They're both in the model, they're both accounted for. So it's Brownian motion. Yeah.
So the motion of the vesicle in the experiment, is it random or persistent?
Well, it depends. It's persistent on a certain length scale, the length scale that you saw, and up to the time window they could possibly observe. If you were to, simulate this on the computer for long times, of course you run into central limit theorem and you get random motion.
And because of the vesicle motion, does the foam get restructured?
Yeah, that you saw. That's the feedback. So as the vesicle moves, that's an important feature of these diffusion reaction systems. They can sense the geometry, and if the geometry changes, the pattern changes, and they can create or change the geometry as well by attaching to the vesicle or by creating these adhesion gradients. Because there's a feedback between geometry and diffusion reaction system. Yeah.
I'll ask one question. Although you spoke in terms of fluxes and concentrations, eventually when a vesicle moves, it's actually mechanics.
Yeah.
And so there are stresses which are giving rise to internal flows and things. So what's the, how does one connect these two?
It's the simplest to explain when you talk about spontaneous curvature, because then the attachment of the protein is used to actually deform the membrane mechanically, right? And so you use the ATP hydrolysis cycle to create mechanical deformation.
Right.
Yeah. That's the link between the chemistry and the mechanics.
Okay, but you haven't, in principle it has to be linked to the fluid flow inside the vesicle also.
Okay, that's yet another thing.
Yeah.
So if that depends now on what all these dimensionless numbers are. how much the fluid flow inside is actually a fluid flow, or whether you can deal with it in terms of volume constraint.
Conservation. Okay.
Yeah, that's open.
Thanks.
We don't know yet.
Okay. Let's thank Erwin again for